Okay, guys, our next unit is we're going to cover the kinetic theory of matter and gas laws, and that's what this recording is sort of designed to be an introductory for. Basic concept is that matter is made of little tiny molecules, little tiny atoms, and as the temperature goes up, they move quicker, they vibrate more quickly. To the point that where eventually a metallic object might melt or a liquid object might boil. So gases in a hot air balloon, they really bounce around much quicker, and the cooler they are, the less they move. This video kind of highlights the three states of matter, the three main states of matter, solids, liquids, and gases. And that's kind of what we're covering. Solids tend to retain their shape, and they don't conform to whatever you put them in. So if you take an ice cube and put it in a round jar, that's still going to stay an ice cube. The liquids will definitely retain the shape of whatever you put them in. So but they do have a distinct volume, so a liter of water is a liter of water no matter what you put it in. And then gases will both conform to the shape of whatever container you put them in, but they can also expand, so they don't have a definite volume. A gas will fill a scuba tank, and that same amount of gas might fill 5 classrooms. So it can be tightly packed and very dense, or it can spread out to fill whatever vessel it's in. 0 degrees Kelvin is when we say that all matter ceases to move. That's what's called absolute zero. And 0 degrees Kelvin is negative 273 degrees Celsius. It's like 0 degrees Celsius is 273 degrees Kelvin, excuse me. Okay, so if you have some notes ready, I would copy down these terms first. The first one is buoyancy. The next one, buoyant force, and it has to do with water displacement. In a little bit we'll go into that, but those are all terms that we associate with what's called Archimedes' principle. Okay, and Archimedes is a man that living on the Mediterranean in ancient Greece, the big challenge was how many clay vessels of wine can I put on a boat and get it across the Mediterranean to Africa, and then I can bring back corn from Africa. So you wanted to get as much wine on a boat as you could, and the big challenge was how much weight can a boat hold up, and Archimedes came up with Archimedes' principle. Basically, it says that the amount of water that's moved out of the way or displaced by a boat, if you took all that water and weighed it, that's how much weight a boat can hold up. So however much water is moved by a boat, that's how much weight that boat can hold up. So that's how we can take an aircraft carrier and basically have a big floating city. People live 2 or 3 years on an aircraft carrier. There's gyms on an aircraft carrier and even markets. So aircraft carriers are huge. So if you change the shape of something, you can actually get it to float. Okay. So the displaced water, if it weighs less than the ball, then the ball's going to sink. But if the displaced water weighs more than the ball, then it's going to float. So you have to make a shape that will displace a lot of water. The force that's holding the water up is called the buoyant force. Okay. So yeah, there are still things that float on water because they're less dense than water. Water has a density of 1 gram per cubic centimeter. So anything that's less dense than that, like styrofoam, it really doesn't matter what shape it's in, it's going to float. We're just talking about things that have a greater density than 1 gram per cubic centimeter. and how they have to, their shape matters, how much water they displace matters. Okay, another principle we're going to talk about in gas laws has to do with the concept, like if you squeeze one end of a toothpaste tube, out the other end comes the toothpaste. And if you squeeze it hard, then it comes out hard. If you squeeze one end of a water balloon, whoop, 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 it bubbles up on the other side. And this is the same property that we use to make hydraulics work. This is what's called Pascal's principle. So the hydraulics operate by taking a liquid and putting force, applying it to a force in a small little area. But that amount of liquid, if it's confined, it will transfer all that force into a larger area, which is why we can step on the brakes and get them to stop. On the far left of this slide, you see a drum pulling in a net. This is the kind of fishing that I used to do up in Alaska, and it's all hydraulics. It's all Pascal's principle. So here's the math behind Pascal's principle, if you want to copy this down. F1 over A1 equals F2 over A2, and I'll show you how that works in just a little bit. So F stands for force, and the units for force are newtons, and A, that stands for area. And the units for A are going to be square meters, or meters squared. So F1 over A1 equals F2 over A2. This is Pascal's principle. That's what we use for hydraulics. So we're going to do a problem real quick together. And I'm going to move this to where you can actually see me do a problem. Okay. So hydraulic brakes use Pascal's principles. We're going to try this. So F1 over A1 equals F2 over A2. And when we get problems like this, usually we'll pick one of these four things and not give it to you. So you have to find it. So we're going to do this problem together. The force applied to the foot is 4 newtons. Okay, so the first force I'm going to put down here is 4 newtons. Okay, that's right here. Okay, that's my F1. All right, and the little container that holds the fluid is 0.04 meters squared. So that's my area. All right, on the other side, I have an area of 0.02 meters squared. So we just want to know how much force that would generate, and we'll do that math by cross multiplying 4 times 0.02. Okay, and then we'll divide it by 0.04. So we get 4 times 0.02. We get 0.08. 4 times 0.02 equals 0.08. And then we go 0.08 divided by 0.04. We get 2 newtons. Okay? So that's just an idea on how that would work. All right, now we're going to progress. And I'll show you guys some video footage of this. This is another concept we're going to talk about, that if you blow over the top of a piece of paper, you can actually get that piece of paper to rise. I can just do that real quickly here. Okay, and that's the same concept that helps us generate lift. I'll show you a video of this too, that we used to do this in class. You take 2 empty aluminum cans, put them together, and you can blow right through the middle of them, and you can get them to approach one another. Okay, this is what the Wright brothers helped to use to discover lift. And this is also a concept called Bernoulli's principle. So if you're going to take down notes, you're going to write down hydraulics. That has to do with Pascal's principle. You'd associate Archimedes' principle with a boat floating on the water. So you could draw a picture of a boat floating on the water and write Archimedes' principle. You could draw a tractor or something like that that uses hydraulics and put Pascal's principle. Here you draw an airplane and you'd write Bernoulli's principle. Yeah. Bernoulli's principle. That's the concept that if air is rushing over the top of a wing, if you see on this slide, it's kind of got the side view of a wing, and air has to travel a great distance over the top of that wing, and that reduces the pressure above it. Kind of like when you blew air over the top of a piece of paper, that reduced the pressure on the top of that paper. If the pressure below that paper remains the same, you create something called lift, okay? Which the Wright brothers stole the design for their airplane wing from a bird's wing. They looked at the great distance over the top of the wing compared to the bottom of the wing that air has to travel, and they realized that reduces the pressure. And that's Bernoulli's principle. We associate flight with Bernoulli's principle. These are all gas laws and gas principles. Okay. All right. So back to square one. If you haven't written it down yet, you want to write the kinetic theory of matter. Okay, and it's based on a couple of different concepts. Key concepts. Particles are in constant motion. So air inside of a balloon is in constant motion. And that creates pressure inside of the balloon. As you heat those particles up, they speed up. Okay? That's kinetic theory. Kinetic means motion, movement. So would air in a balloon behave the same way at the beach as it would at the top of Mount Hood? Now we're talking about air pressure. There's less pressure on top of Mount Hood than there is at the beach because there's more air on top of you at the beach. So what would that do to a balloon? So the next thing that you'll want to write down, you've written down Archimedes' principle, you've written down Pascal's principle, you've written down Bernoulli's principle. Now you want to write down Boyle's law. Okay? Boyle's law connects pressure and volume. So you're going to have a little tiny volume under high pressure and a big, big volume under low pressure. So a balloon at the top of a mountain is going to be huge. That same balloon would be quite small down at sea level. The bubbles that the scuba diver blows way, way down there are going to be tiny, but they get bigger and bigger and bigger. Right? So you have 100 kilopascals of pressure on top of you at the beach, and at Mount Hood you have 30 kilopascals of pressure. And we'll learn to do some math. We're kind of running out of time, but if we had 1 liter of air, then the equation that we're going to use, let me crank that math out real quick. I'm running out of time, so I'm going to go kind of quick. You have an equation that says P1 times V1 equals P2 times V2. P1 V1 equals P2 V2. And this problem says that at the beach there's 100 kilopascals, so that's 100 kilopascals, and Mount Hood's 30 kilopascals. Okay, and then and so if the volume is 1 liter at sea level, okay, so we go 100 times 1 liter, what would that equal here? Okay, so 100 times 1 equals 30 times something. All right, so you'd multiply 100 times 1, you get 100, and then you would divide it by 30, and that would give you the volume on the top of Mount Hood. Okay, I know I went kind of quick there. I'm kind of in a hurry. I'm running out of